All right, I guess we can get started. Welcome back. It's the 15th lecture of the condensed matter course. When last we left off, we were talking about trying to approximately solve the Schrodinger equation for electrons in solids. And the method we were talking about using was the nearly free electron model. Nearly free electrons. The general idea being that we're going to write our Hamiltonian as some bare, just regular, non-interacting electron plane wave Hamiltonian plus some potential. So the eigenstates of this in a plane wave k is h bar squared k squared over 2m, just your regular electron Hamiltonian. But then here we have some periodic potential, which we're going to eventually consider to be weak, hence the name nearly free, weak potential. And the idea that we took from scattering theory is that the matrix element between some k and k prime from this periodic potential has to be 0 if k minus k prime is not an element of the reciprocal lattice, and we'll call it v sub g if k prime minus k is an element of the reciprocal lattice. So then we treated the potential v as a weak perturbation, and in second order perturbation theory, second order pert, we found that the energy of the plane wave k starts out as the bare energy of the plane wave k plus v sub 0, the 0th Fourier mode of the potential. That's just an overall shift of all of the plane wave energies. That's uninteresting. People sometimes just drop it all together because it's just a constant. But the interesting piece is the sum over all reciprocal lattice vectors, v sub g squared over energy of k minus energy naught of k plus g. So this is our second order perturbation theory expression. And the thing that one has to worry about is that the denominator can be either 0 or close to 0. And that happens when, so this diverges when we have k, absolute k, being equal to absolute k plus g, so that the energy of k and energy of k plus g are the same. And that is equal to the same condition as k and k plus g being on BZ boundary, Bron zone boundary. So in that case, we have a problem. Our second order perturbation theory doesn't work because of this degeneracy. And what we're supposed to do is we're supposed to use degenerate perturbation theory. Degenerate Pert theory. Resisting all urges to make jokes about the word degenerate, which probably have been made hundreds of times before. The general rules of degenerate perturbation theory are that you should take the states that are causing you trouble, the states that are giving you the divergence, separate those out from all the other states in the system, and just diagonalize the Hamiltonian within the space of those problematic states. So for us, the states that are causing us trouble are states k and k plus g for some particular g. So we'll write our trial wave function. Actually, maybe we'll be a little bit more general and assume k and k plus g, assume these are near a Bron zone boundary, near a BZ boundary. So it may not be an actual divergence. It can just be a near divergence. It's still bad enough to cause us to not trust our second order perturbation theory anymore and require us to use degenerate perturbation theory, even though if it's not it's not a 0 in the denominator, it's just something close to 0 in the denominator. The general scheme is to write a trial wave function, which is going to be sum of the problematic kets. So k and k plus g. We may take some linear sum of these two. And in the usual way, we will try to find the best linear combination of these two kets in order to get our lowest energy state within this space. So we've done this a couple times before. The way one does that is you write down Hamiltonian, an effective Hamiltonian equation, sum over m, h, and m, phi m equals E phi n. This should look familiar from what we did when we solved the tight binding model for the covalent bond. Here, this H and M is a 2x2 matrix where n and m are chosen from k and k plus g. This is how you do degenerate perturbation theory. You just restrict the space of states to the space of degenerate states who are causing trouble in the second order perturbation theory. All right, so the only thing we need to do now in order to follow this prescription is we need to write out the matrix elements H. So for example, we have K, H, K. That's one of the 4 matrix elements. We can write that as K, H naught, K plus K, V, K, since our Hamiltonian is made up of the H naught part and the V part. This part is easy. This is just E naught of K. And this part is V naught, just the overall constant energy shift. The subscript is 0 because K minus K prime is 0. Similarly, K plus G, H, K plus G is equal to E naught of K plus G plus V naught again. The more interesting term is the term, the off-diagonal terms of the 2 by 2 matrix, K plus G, H, K. So let's write out the pieces of this. We have first K plus G, H naught, K. And the second piece is K plus G, V, K. Well, the first part, this is easy because this would be H naught. K is an eigenstate of H naught, so we can just pull out an E naught sub K and get K plus G, K. But this is 0 because these are 2 orthogonal plane waves, so that's 0. That first term is 0. The second term is we've defined that as being V sub G. We're allowed to scatter from K to K plus G via the scattering potential G, and way up at the top. Oops, I scrolled it off the top. Yeah, there it is on the top. The V sub G of K minus K prime is an element of G. So we call this thing V sub G. So what we have now is, and also, so this thing is going to be, overall, this is going to be V sub G. And we can do the other last matrix element, H, K plus G, which, using the same argument, is V sub minus G, or V sub G star. It's complex conjugate of its partner up here. So now we have our Hamiltonian, our 2 by 2 matrix we can write down, which is E naught of K plus V naught. And we have V sub G up here, maybe star here, V sub G down here, and E naught K plus G plus V naught. So far so good? Everyone happy with this? More or less? Did this go by too quickly? Yeah, happy? Okay, good. All right, so for homework, problem set 4, I think, you're going to actually solve this in general for a K near the Brillouin zone boundary, which makes the algebra a little bit more complicated. But what we're going to do here is we're going to simplify our algebra a little bit and assume K is right on the Brillouin zone boundary. Assume K and K plus G are on BZ boundary, just to make the algebra a little bit easier. So that means that E naught of K equals E naught of K plus G. They have the same energy, so we're right on the degenerate point. In which case, this is a very simple matrix. It has 2 elements which are the same along the diagonal, and then complex conjugate matrices elements on the off diagonal. And the energies are then E naught of K plus V naught plus or minus absolute Vg. And that's our answer. So what does this mean? Let's maybe draw it here. So we have, here's K, here's energy, E. And before we add the perturbation, we have a nice parabola. We have the usual, let's see if we can draw it like this. So this is the usual parabola, which is E naught of K equals h bar squared K squared over 2m. So that's the free electron parabola. Then we can put down the periodic potential. It has some Brillouin zone boundary for this. So it has some lattice constant A. It's Brillouin zone boundaries at pi over A and minus pi over A. Because I have more Brillouin zone boundaries at minus 2 pi over A and 2 pi over A. here. So here, at this point, this Brillouin zone boundary, minus pi over a and pi over a, you can scatter between them by this reciprocal lattice vector g equals 2 pi over a, can get you from minus pi over a to pi over a. So in second order perturbation theory, you would discover that if you analyze this point here or this point here, you would get a divergence in second order perturbation theory, and we would have to use degenerate perturbation theory in order to figure out what happens to these points. And what we just derived is that in fact they split in energy, and the way it's going to look is that this is going to shift down, and then this will shift up a little bit, so that in fact you open up a little gap between the things coming in from the left and the things coming in from the right, and its size is 2 absolute Vg here. And the same thing happens over on this side, like this. Opens up a gap of size 2 absolute Vg. And the same thing would happen up here, where you can scatter from Brillouin zone boundary to Brillouin zone boundary by g equals 4 pi over a. And here a gap would open up at the Brillouin zone boundary here, and a gap would open up at the Brillouin zone boundary here. Okay? So since I've drawn that fairly badly, I was prepared for this, and I have a slide. So here's the same picture in extended zone scheme. This is starts with the bare parabola, the nice free electron parabola. And then when you add the periodic potential, the major effect of the periodic potential is near the Brillouin zone boundary, where it opens up this gap. You notice that the states inside the Brillouin zone boundary get pushed down in energy by a little bit, and they get pushed down more if they're closer to the Brillouin zone boundary, because as you're closer to the Brillouin zone boundary, if you think in second order perturbation theory, that's where the divergence is getting worse and worse and worse. It doesn't actually diverge, but still the perturbation is becoming more and more important as you get closer to the Brillouin zone boundary. So the gap opens up, things get pushed down more as you get close to the Brillouin zone boundary. And then if you're just outside the Brillouin zone boundary, things get pushed up, and you open up this little gap at the Brillouin zone boundary. Same thing over here. Now, we're perfectly entitled to view the same thing in reduced zone scheme, where we take this piece of the spectrum and we shift it over by 2 pi over a, so it's over here, and we take this piece of the spectrum, we shift it over by 2 pi over a in the other direction until it's over here, and we view everything within the first Brillouin zone, but now we have two bands within the first Brillouin zone, so we have a lowest band and we have a higher band. And this looks a little bit like what we found when we studied the tight binding model a couple weeks back. We had when we had two orbitals per unit cell, there were two bands at two values of two eigenstates at each possible value of k, which is what we have here. And the structure looks more or less similar. You have a low band, a high band, a gap opening at the Brillouin zone boundary. However, we're really coming at this from a very complementary direction. When we did tight binding model, we started by taking a bunch of orbitals, and then we weakly coupled them together and allowed the electrons to hop from one orbital to the next to the next. Here, we did the opposite. We started with a plane wave, and we weakly perturbed it with a periodic potential. But either way you look at it, you get the same physics of separate bands, gaps at the Brillouin zone boundary. If you look at it from the nearly free electron model, though, really this picture, you can see in this picture, it's actually just a free electron parabola with small perturbations at the Brillouin zone boundary. So this parabola is sort of continued in the second band. So this piece of the parabola is sort of reflected back and continued in the second band, and they don't quite touch because of the gap opening up. But the curvature of this band near the bottom is actually given by the free electron mass. So the thing that causes the curvature at the bottom of your parabola, that's dependent on the free electron mass, not on anything else. So we really should view this bottom of the band, which looks like a parabola, as just being essentially free electrons. Okay, so a question that's fairly important at this point is, maybe I'll put it over here, is why the gap? Why the gap? Mind the gap. Why the gap? Okay, so in order to understand why it is that this gap is opening up at the Brillouin zone boundary in a different language, it's useful to give an example. So examine a particular potential. I'll choose v of x, and we're going to do this in one dimension. Actually, this is one dimension also. I should have mentioned that. This is in one dimension. This is a more general equation, which will hold in any dimension. We're going to do this example in one dimension also. So v of x, we'll choose it to be 2 v twiddle cosine 2 pi over A times x. That's a nice periodic potential. Maybe I'll even draw that periodic potential. Everyone probably knows what it looks like, but I'll draw it anyway. So, okay, here's our axis x. Maybe we'll put A here, minus A out here. And the cosine potential looks like this, and looks like this. So this is V of x. And the lattice constant is A. The periodicity is A. And the reason I've chosen this particular simple cosine potential is because it has nice Fourier modes. V sub 2 pi over A equals V sub minus 2 pi over A equals V twiddle, and all other V sub G are equal to 0. So it only has two Fourier modes which are non-zero, and they're both given by V twiddle. All right, so now let's think about what this is going to do. What this can do is it can scatter by V sub G only for G is 2 pi over A. So in this picture, it means it can scatter from this point to this point by G. These are the 2 points in degenerate perturbation theory that can mix with each other. This point at K equals minus pi over A and K equals plus pi over A. So the scattering we have to worry about is from K equals minus pi over A and to K equals plus pi over A being scattered back and forth by this potential. So it can scatter back and forth between those two wave vectors, which are right on the Browne-zone boundary. So in real space, if I think about x, k representations of these kets, these things are e to the I pi over ax and e to the minus I pi over ax. And I'll use that notation. If we then diagonalize this Hamiltonian in this space, what we'll get is we'll get our two eigenvalues, or our two eigenfunctions. Our psi plus will be e to the I pi over a x plus e to the minus I pi over a x, and its energy E plus is E sub pi over a naught plus V twiddle. And the other eigenstate, psi minus, is e to the I pi over a x minus e to the minus I pi over a x. And its energy, E minus, is E naught pi over a minus V twiddle. So one of these linear combinations of these plane waves is getting pushed up in energy. One of them is getting pushed down in energy by V twiddle. So again, we have these two plane waves, one going left, one going right. They're getting mixed together by this scattering potential, by this periodic potential. And one of the two eigenstates has been pushed up in energy. One of them has been pushed down in energy. Why is that? Well, let's see if we can figure that out. Let's take psi plus, square it, so we get the probability density. So this is the density, the probability density, prob density, psi plus squared, which is proportional to cosine squared of pi over ax, and psi minus squared will be proportional to sine squared of pi over ax. And let's plot those on this same figure. So let's see, psi plus looks like this. It's cosine squared of this psi plus squared. And then psi minus looks like this. Psi minus squared looks like that. So they have their probability density is in different places along the in the positional space. They're in different places along the axis, and because of this, the psi plus squared sees, I'm putting that in quotes, sees mostly positive v of x. So you see where psi plus is great, where it's very large, that's where v of x is positive, and when psi plus is small is where v of x is negative. So that means psi plus, E plus, is pushed up in energy, is pushed up because it's experiencing mostly the positive potential. Whereas in comparison, psi minus squared sees mostly negative v. V of x, because psi minus is large where V of x happens to be negative. And so it's pushed down. E minus is pushed down in energy. So let's sort of think about this a little bit more carefully. So what's going on is we have this space which has a left-going wave and a right-going wave. That's the space of the degenerate perturbation theory. And with the variational principle, what we're supposed to do is we're supposed to put them together in a way that will, to get the ground state, we're supposed to put them together in a way that will minimize the total energy. And the way you minimize the total energy to get the ground state is you put them together such that you get a psi minus, because psi minus has its maximum where V of x is negative, and that pushes down its energy. Therefore, it pushes it down as much as possible. Therefore, it's the ground state eigenstate. And conversely, psi plus has pushed up its energy as much as possible, as high as possible, by putting its density where the potential is positive. So is that clear why that's going on? All right. Good. So do you ever read the examiner reports? Do people read the examiner reports? Have you never noticed they're really nasty? I think it's an unwritten requirement. The examining reports have to be really nasty. I've never been on the examination committee yet. One day my time will come and I'll probably read the rule, the unwritten rule somewhere on some tablet that says you must be nasty. Okay, so there was a question that came up about this nearly free electron model. It came up about 4 years ago, and it really threw a lot of people. So I'm going to go through the physics of what was involved in there, which isn't too much more complicated than what we did, but it's something that a lot of people found rather unexpected. So I'm going to explain more or less what was going on in that problem. So when you run into it someday, it won't trouble you. So we're going to consider a square two-dimensional lattice. And I'm drawing reciprocal space. This is a reciprocal lattice. So square 2D lattice. Square 2D lattice. And the reciprocal space of a square lattice is also square. So I'm going to draw the Broughton zone. So this is k equals 0 here in the center. And the first Broughton zone is this square here. And this point here in the corner is pi over a, pi over a. Okay? Now, the first thing this question asks you to do is find out what happens when you add a periodic potential, what happens to a point here on the Broughton zone boundary. Okay, so that's basically exactly what we just did. That point there, due to the periodic potential, it can mix in with this point over here. These 2 points are separated by a reciprocal lattice vector. This is a reciprocal lattice vector, 2 pi over a. So these two can mix together via scattering. They have the same energy because they're the same distance from k equals 0. They have the same amplitude of their k. So this condition holds, Ek equals Ek plus g. So they mix together, and it's exactly the same calculation we just did. It's just, it's really a two-dimensional model, but we're just considering this cut through 2 dimensions. There will be a gap opening up at the Broughton zone boundary at this point, at this point. So that much is simple, or should be simple, I hope. It's exactly like what we did in 2 dimensions, in 1 dimension, but now in 2 dimensions. The thing that was complicated is what happens if you consider this point up here in the corner. So let's call this point 1. So now what we have to do is we have to ask, where do the divergences come in second-order perturbation theory? Well, this point 1 can scatter by a reciprocal lattice vector to this point 2, but it can also scatter by a reciprocal lattice vector to this point 3, and this is also a reciprocal lattice vector to this point 4. And in fact, 4 can scatter to 3, 4 can scatter to 2, 2 can scatter to 3. They can all scatter to each other by reciprocal lattice vectors. Those vectors in k-space are all reciprocal lattice vectors, and they're all allowed to mix to each other, and they all have the same energy before you add the perturbation. So when you do your degenerate perturbation theory, you'll find a bunch of these things, a bunch of these denominators that are all 0. Okay? If you're considering this point, scattering to here, there'll be a denominator 0, scattering to here, all 0. So the way you handle this is you have to write your trial wave function that includes all of these wave vectors, psi1 k1 plus phi2 k2 plus phi3 k3 plus phi4 k4. All of these things have to be included in your trial wave function, and then your Hamiltonian is then a 4x4 matrix, which includes all possibilities of how you scatter back and forth between all of those 4 points. Okay, so that was what was asked on the in the exam, and a lot of people got thrown by it, even though it's not really that much more complicated. Okay, good, happy with that. All right, let's do a real example here. In 3D, in real life, we have things like FCC lattices. This is, as we discussed a couple days ago, this is the Broughton zone of the FCC lattice. The gamma point is the point at k equals 0 in the middle. The x point is at the Broughton zone boundary in the middle of this square face here in the kx direction. The L point is in the Broughton zone boundary in the middle of this hexagonal face, for example. And the material we're going to think about is the material silicon carbide. Silicon carbide is actually it's another important industrial material. It has this structure here. It's FCC with a basis. So the yellows are silicons and the blues are carbon. The silicon can be taken at 0, 0, 0, and the carbon at 1 quarter, 1 quarter, 1 quarter. We've seen this structure before. This is this zinc blend structure. Zinc sulfide, gallium arsenide takes the same structure. Silicon carbide takes this structure. It's a very common structure. Okay, now, all right, so here, let's see if we can understand how this picture, this complicated picture of all the eigenstates for electrons can come out of nearly free electron models. So let's look down at the lowest energy. The lowest energy here, we have the gamma point. That's at k equals 0. Gamma is another name for k equals 0. And as you go out in the Broughton zone towards the point x, you see this thing that looks kind of like a parabola. And if you back up, that's, oops, back here. So it looks kind of like this parabola here. And that's exactly what you're seeing here. This is the free electron parabola coming out from k equals 0. And when you get to the Broughton zone boundary, there's a gap opening up, and this is the second half of the parabola going up. All right, let's back. Not up there. Here it is. So here's the second half of the parabola up here, just like the second half of the parabola is here. And you could go off in another direction, so going from gamma out to the L point, again you have a parabola, and then a slightly bigger gap in the L direction, and here's the second half of the parabola here. Okay, so it's basically free electron model. And if you measure the curvature down at the bottom of the band near gamma equals 0, you get basically the mass of the free electron. It's not exactly the mass of the free electron, but it's pretty close to the mass of the free electron within 30% or 20% or something. So it really tells you that what's going on near the bottom there is basically free plane wave physics, just perturbed slightly by the scattering potential that at the x point scatters you across the Broughton zone and opens up this gap. Is that clear so far? All right. So when we're on the subject of really nasty exam questions, about 6 years ago there was an exam question about this that not a single student got right, and the examiner went, berserk on that and ranted about awful students and so forth. But that's just that's required of them to do. But the question was actually quite difficult, and I think it was, I'm going to explain to you what the question was about. It's something that if you hadn't seen it before, it would be very, very hard to figure it out. But I guess the expectation was you were supposed to be taught it, and I don't think anyone taught it. So now I'm going to teach it, so if it comes up, you'll all know it. So the question was about comparing something like this to something like silicon. So this is silicon here. It looks almost exactly like silicon carbide. The only difference is instead of carbon at 1 quarter, 1 quarter, 1 quarter, you replace those carbons with another silicon. So it's all silicon. Silicon at 0, 0, 0, and silicon at 1 quarter, 1 quarter, 1 quarter. We've seen this structure before too. This is the same structure as diamond. Silicon and diamond structure are equivalent. Same crystal structure. And actually, if you look at the two eigenenergy spectra here of K across the bottom and energy up top, that they're actually silicon and silicon carbide. They look almost, well, I wouldn't say identical, but extremely similar. A lot of the features in one are there in the other as well. So for example, here you have the same parabola, but you'll notice there's one sort of shocking difference here, that there's no gap at the Broughton zone boundary here, at this x point. The x points here, the parabolas come together, and they don't split at all. And so what one is supposed to deduce is, in fact, that there's no backscattering at the x point at all. For some reason in silicon, you do not get scattering at the x point. Okay? So now we're going to try to figure out why that is. So first of all, for the chocolate bar, the scattering at the x point goes from an x point on one side of the Broughton zone to the opposite side of the Broughton zone. what are the Miller indices associated with that reciprocal lattice vector? What? No one? No, this is really good. 001 is a very good guess, but it's not right. Does anyone want another guess? No. Okay. No, so 001 is the right direction, or actually I guess it's in the x direction, or 100 if you prefer, if you're doing in the x direction. That would be pointing in the right direction, because x is in the kx direction and minus x would be in the opposite kx direction. So it would be in the 100 direction that you're scattering, or the 001 if you're going the other way. So that's the right direction, but it's not 100. And the reason it's not 100 is because 100 is not a reciprocal lattice vector for FCC lattice. And you'll remember, back to this picture here, that you remember that 100 is a reciprocal lattice for the simple cubic lattice. If you define the planes by the 100 Miller index, you get these planes here. But the FCC lattice has some additional lattice points in the middle. So 100 does not get all the lattice points. Therefore, it is not a reciprocal lattice vector for the FCC lattice. 200 is the smallest reciprocal lattice vector in that direction. So here, scattering from x to minus x, I'll even write that down. So x to minus x scattering is 200 for silicon. Well, actually, for any FCC lattice, x to minus x is 200. Okay, so we've gotten that far. Now the question is, why is it that we don't get any scattering at 200 Miller index? Does anyone want to guess of that? I have one more of these left. What was it? I can't hear. Who? The mass. Yeah. Well, they're both silicons. So yeah. So that doesn't do it for you. Any other?
It's not an FCC lattice, so the reciprocal lattice vectors would be different.
It is FCC lattice. It's an FCC lattice with a basis. So I'm not going to give it to you for that, but it's close to that. So maybe I'd give you half of this, but I don't know how to do that. So it's not pure. It's not just an FCC lattice, and that's the point. That you have to keep track of the lattice and the basis to find out if there's scattering. So let's think back to. I mean, it is an FCC lattice, but it's a lattice. The silicon is a lattice plus times a basis. So if we think about what we learned about scattering from X-ray scattering, remember that S is S lattice times S basis. Right? And S is what gives you the amplitude of scattering. Right? If we square S, you get the amplitude of scattering. This worked for X-rays, and it will work for electrons as well. So S lattice, that enforces selection rules. Enforce selection rules. And 200 actually satisfies the selection rule for an FCC lattice. All even or all odd for FCC. 200 is all even, so we're okay with that. So that's not going to vanish. But let's look at S basis. S basis, you'll recall, is sum over atoms alpha in unit cell of e to the f sub alpha, the form factor e to the I g dot r alpha. And if we do this for silicon, we'll get f silicon, and then it'll be 1 for the point at 000. And then we'll get e to the 2 pi I, and the Miller indices of the scattering, 200 times the position of the lattice point, 1 quarter, 1 quarter, 1 quarter, like that. Does this look familiar from our X-ray scattering adventures? Yeah, okay. So you'll notice that this thing here is actually minus 1. So S basis is 0. So there's no backscattering in silicon in the 200 direction, because there's, I'll give this to you anyway because, oops, because I don't want to keep it myself, because then I'll eat it and I've been gaining weight. So okay, so you don't get backscattering in the 200 by 200 because what this is telling you is that there's exact destructive interference between the scattering of the two silicons in the unit cell. That they'll both scatter, but then you get exact destructive interference by them, and so in fact you get no net scattering at the end of the day. And this physics is actually it occurs for X-rays in silicon. There's no scattering of X-rays for silicon in the 2, 0, 0 direction. It occurs for electrons. There's no backscattering at the X point for electrons in silicon. It also occurs for phonons. Let's see, here's the phonon spectrum for silicon. This looks a whole lot like the phonon spectrum for diamond, not coincidentally, because it's the same crystal structure. So here's the silicon phonon spectrum. It has, so we had this previously. There's 6 phonons at every K vector because there are 2 atoms per primitive unit cell, and each one moves in 3 directions. So there's 6 phonons, 1, 2, 3, 4, 5, 6. And 3 of them are acoustic, coming down here. Now you'll notice if you look at this point here at the X point, in this picture, silicon carbide, a gap has opened up. In this picture, a gap has not opened up. And it's coming from essentially the same physics. Even with phonon waves, that in the 2, 0, 0 direction, there's not backscattering, therefore you don't have an opening of a gap. Whereas in silicon carbide, you don't have perfect cancellation because this term would have F silicon, this term would have F carbon. Those don't equal each other, so you would still have backscattering and you'd have a gap opening up at the Brillouin zone boundary. Okay? So I realize this is a little bit complicated, but it was on an exam, and hopefully, if it comes up on an exam again, people will be able to get it right. But I do admit that if you've never seen that before, it's something that's pretty hard to figure out. So, all right. So, having basically discussed everything that we need to know about the nearly free electron model, we can now move on to talking about generally band theory, band structure, band theory of electrons. So these complicated pictures, here there's silicon carbide again, with its complicated picture of all its eigenstates at every K. So let's, we started talking about band theory when we talked about the tight binding model. Maybe let's draw a picture of some bands, like over here. So here's energy, here's K in this direction. So I'll draw the Brillouin zone. There's a Brillouin zone from minus pi over A to pi over A. And then you might have some bands that look like this, and then a higher band that looks like this, and maybe some higher bands up here as well. Now, some things that we mentioned when we talked about the tight binding model is that if you have a filled band and a gap plus gap, you have an insulator equals insulator. I'm repeating this because it's fairly important. So if we fill a band, we fill, say, this band, and a gap to the next band, we have an insulator. And the reason this is an insulator is because there's basically no freedom of where to put your electrons. Unless you overcome the gap to the next band, which could be a lot of energy required to get up to the next band, you can't rearrange the electrons at all. They can't absorb any heat. They can't change their momentum because all the momentum states are already filled. So it's basically just completely inert. So I'll write that down. It's inert. And if you have 2 bands that are completely filled, again, you'll have and a gap to the next band. It will also be an insulator. A little bit of nomenclature which is useful is the highest filled band is usually called the valence band. So here, this would be valence band. And the lowest empty band is known as the conduction band. Which would also be a really good name for a rock group. So if anyone makes a rock group, I'm suggesting a name. Conduction band. Okay. So another important statement that insulator with small gap, gap is known as a semiconductor. And small here is sort of less than about 4 electron volts equals, this is known as a semiconductor. And the reason for this nomenclature is that if the gap is sufficiently small, then at 0 temperature, this would still be a really good insulator. But at room temperature, 300 Kelvin, if the gap is less than about 4 electron volts, then a few electrons will still be able to get thermally excited from the filled band into the empty band. So you'll have a couple electrons running around free, just thermally occupying the conduction band, and they will carry some amount of current. That you'll get a couple of electrons running around up here, and that will allow them to carry some small amount of current, some small amount of conductivity. So it's a semiconductor. It conducts sort of conducts poorly, but it conducts. Similarly, it can absorb small amounts of heat, but not a lot of heat, because only a very few electrons can be rearranged. Okay? Does that make sense? Yeah? Okay. So this picture of silicon carbide, these bands here are all filled. The Fermi energy, or the chemical potential, lies in the middle of this gap. So you would say that it's an insulator or a semiconductor. And if you sort of look at the difference in energy between this point, the lowest point of the conduction band, and this point here, which is the highest point of the valence band, it's a little less than 4 eV, so we would say silicon carbide is a semiconductor. Okay? Now, something else that we mentioned when we talked about tight binding model is that counting electrons in states is rather important to figuring out if you have a filled band or not. If you have n unit cells in your system, then you have n k states, but then you have times 2 spin states per k means that 2n electrons will fill a band. And this, to get 2n electrons, you need 2 electrons per unit cell. So that you expect that if you have any even number of electrons per unit cell, you would expect that you can fill integer number of bands. So let's take the case of silicon carbide, for example. So silicon carbide. So silicon and carbide both have valence 4. So silicon and carbon both valence 4. Valence equals 4, which means we should count 4 electrons for each of them. Okay? If you wanted to count all of so why am I only counting 4 instead of all of their electrons? The reason is because we really generally only count the electrons in the farthest out shell, because any of the farther in shells are completely inert. They're just way buried at much, much lower energies. But if you wanted to count their filled shells as well, you would discover that their filled shells are all even as well. So we would still have an even number of electrons both for silicon and carbon. So the primitive unit cell here, in this picture has 8 electrons total. 1 silicon atom, 1 carbon atom, each carrying 4 electrons. So we should fill 4 bands. I think I asked the same question about diamond about a week ago or more. And in fact, if you count the number of bands here, which are below the Fermi energy, there are 4 of them. 1, 2, 3, 4, and they're all filled. We do have this little bit of a confusion here that if you count here, it would look like there's only 3. But if you look more carefully, you'll notice that in fact there's 2 bands here which come together and have the same energy. So this one is actually 2 bands that just happen to have the same energy. Here they have different energies, so you can count that there's actually 4 of them. So in silicon carbide, all these 4 bands are filled, and all these bands up here are empty. Good? Good? Yes? Yes? Okay, good. All right. Now, in contrast, we have metals have part-filled bands. Which is almost always true. Mostly, maybe I'll write mostly true. Either today or next time we'll discuss about why it's only mostly true. Mostly true for odd number of electrons per unit cell. For example, if we had a picture like this, so here's the Brillouin zone, here's a band, here's a band. Suppose we have 1 electron per unit cell. That would be enough to half fill the lowest band. And so we have a part-filled band. This is 1 electron per unit cell. part-filled band here. And we would call this thing a metal because since the band is only part-filled, we can make low-energy excitations by taking an electron from the filled point to the unfilled point, arbitrarily low energy. We can also change the momentum of these filled states by just taking some of the electrons from over here and moving them over here at very low energy cost, or just slightly shifting the entire picture, slightly shifting it to the right to fill a couple more states over here and a fewer states over here. And since you're changing the momentum, you're actually adding current in that case. So by changing the momentum of all these electrons, you've actually changed the total electrical current in that system. And so since it can carry current, we call it a metal. However, metals can also occur. Metals also occur with even number of electrons per unit cell. Also something I mentioned a couple weeks ago when we discussed tight binding model. The way that happens is here's your Brillouin zone. If you have a lowest band that looks kind of like this, and then you have a higher band that dips down like this, and you had, say, 2 electrons per unit cell, that would be just enough electrons to fill one band, but you could choose to fill this entire band if you wanted to, this entire lowest band, but that would be energetically unfavorable compared to partially filling both of the bands. So instead, it's better to partially fill this and partially fill this instead of filling these higher energy states in this lower band. Does that make sense? Yes? Yes, okay, good. So in this case, if bands overlap, I'll write this, if bands overlap. And it looks a little unnatural when I draw it this way, but if you look back to the silicon carbide band structure here, you could certainly imagine in your head that this minimum just dipped down a little bit further, and this maximum came up just a little bit further. And if that were true, so that this minimum went below this Fermi energy and this went above the Fermi energy, then some of the electrons that was previously in this band that was filled would then go into this band, which was empty, to lower the energy. Okay? So one thing that's really important to keep track of is how big are the gaps between bands. So if the gaps between the bands are really huge, then you're not going to have this situation ever occur. If the bands are sufficiently far apart, then they're not going to overlap. So how big are gaps? How big are gaps? Big are gaps between bands. Gaps between bands. Question? Well, we had different ways of describing how we understand the band structure. One way of describing it was from tight binding. In the tight binding picture, recall that each band comes from an atomic orbital, is from an atomic orbital, with energy E, with energy, it's called E sub I, and the bandwidth is from hopping. Hopping T. So if the original atomic orbitals are very well spaced apart from each other and the hopping is small, then the bands don't have a chance to overlap because they initially start very far apart from each other, and the hopping is what spreads the bands out from a single energy into a band. So if the hopping is small and the energy spacing is large, then the bands won't overlap. So that's one way of understanding it. That's sort of a natural way to understand why it is that something like noble gases, when they form crystals, they're insulators, because the hopping between noble gases is essentially zero. So these original atomic orbitals, they're spaced a little bit, but the hopping that spreads out these orbitals into bands is negligible, so they don't form very wide bands, and so the bands never overlap. So that's one way of understanding it, but in a nearly free model, nearly free, the gaps at the Brillouin zone boundary, at BZ boundary, are from the periodic potential, from potential V of x. So if you know that the periodic potential is strong, you should expect gaps that are pretty big opening up at the Bronze zone boundary, whereas if the potential is fairly weak, then you expect not to have big gaps at the Bronze zone boundary. All right. I think maybe, although we have 2 minutes left, I think maybe we should stop there and we'll pick up more on band theory tomorrow.